recap to the last part of the last lecture. So we saw that coupling fermions to gauge fields gives us a way of writing gauge invariant Lagrangians. I'm going to review this last part here on non-abelian gauge symmetries and how fermion fields interact with gauge fields. So we began with the Lagrangian for n non-interacting Dirac fields, and this Lagrangian has a unitary symmetry group, so UN symmetry. And in fact, as we've seen, it actually has UN left times UN right symmetry. And the question was, can we gauge the symmetry? And the idea is then to introduce a covariant derivative such that the covariant derivative of the field transforms in the same representation as the field itself. And then if we were able to define such a thing, then the Lagrangian at the bottom, where we've replaced the ordinary derivative with the covariant derivative, that would be gauge invariant. And so the idea is to introduce a matrix of gauge fields, one for every generator of the Lie algebra of the symmetry group. And that gauge field is just a linear combination of the generators, where the coefficients A, mu, P are a different gauge field for each value of P. So if we were gauging the full symmetry group, we would have n squared gauge fields here. But it might be that we're interested in gauging just a subgroup of that, for example, just the SUN part. And then we would have, if we were gauging SUN, we would just look at the traceless emission generators, and we would have n squared minus 1 gauge fields. So we looked at the example of SU2 gauge symmetry. That's the basic example, which we can then generalize to any gauge symmetry. So here, psi1 is a 4-component Dirac field, and psi2 is also a 4-component Dirac field. And we're choosing them to transform in the fundamental representation of SU2, as written in the middle there. And then with that definition, the covariant derivative is given explicitly here, and we've introduced a gauge field for each of the 3 generators of SU2. And we've written it out explicitly as a 2x2 matrix to emphasize that we can we're able to calculate this covariant derivative acting on the SU2 doublet of fields psi1 and psi2. And so this is the Lagrangian then, as we've defined it, and then hopefully you've been able to work out the interaction terms explicitly. And this example is important because in the standard model, the left-handed quarks and left-handed leptons pair up into these doublets under SU2, under the SU2 gauge symmetry of the standard model. So we're going to look at that in more detail a little bit later on today. Okay. And here I note that it's only the left-handed components of the quark and lepton fields which transform under SU2. The right-handed ones do not, which means that the right-handed quarks and leptons don't couple to the SU2 gauge bosons, which are the W bosons. And that's an explicit violation of the parity symmetry by the standard model. So the sort of important calculation really to demonstrate the gauge invariance is the following calculation that we did in detail. And the gauge transformation of the non-abelian SU2 gauge bosons is given in the middle of the blackboard there. So you see that if you look at the formula at the bottom, the non-abelian gauge field transforms as U times A mu plus I d mu, all divided by the coupling constant G, and all multiplied by U dagger, which is the more general formula. Sorry, I have to close the door because there's some noise. And it's important in this formula that the derivative piece is actually acting on the matrix on the right-hand side. So we didn't do the full calculation at the level of the group, which is a bit more involved, but we looked at it infinitesimally. So at the level of the Lie algebra transformation. So if we take the formula from here and we expand out U to first order in alpha and U dagger to first order in alpha, calculate the derivative, and we'll get a bunch of terms. So this first line over here, the first term is just the identity term multiplied by the gauge field, and the second term is the derivative acting on the infinitesimal gauge transformation. The other two terms in the second line, we see that we get a commutator between the gauge transformation parameters and the gauge field itself. And where do they come from? Yeah, so they just come from the fact that you've got you have U on the left expanded out and then multiplied by the gauge field, and then you've got U dagger on the right expanded out and multiplied by the gauge field. But that comes with a minus sign because it's U dagger, and that generates a commutator. So with that in mind, so we've now got the transformation of the gauge field and the transformation of the fermion fields. That's the information that we need to compute the change in the covariant derivative of the fermion doublet. So let's expand. I mean, that's so on this page we're doing the calculation in detail. So we write so we have the covariant derivative, and then I mean, so first of all we compute change in the covariant derivative, and then we'll apply the change in the covariant derivative to the transformed fermion field. So the change in the covariant derivative is just by substituting the change in the gauge field. So we get these terms over here. And then this is the change in the fermion field. So I've written that out in the two lines below. So first we've got the covariant derivative acting on the transformed fermion field, plus the first derivative term from the first line at the top. And then we've got all of these terms here. So the commutator term just acting on the field. And the one of the terms coming from the which term is this? Sorry. Who can remind me where this term comes from? Yes, so yeah, well, is going on here is that this is actually coming from the covariant derivative. I believe so. So this is the gauge field term coming from the action of the covariant derivative on the transformed field. So then one of these terms cancels with this term because it appears, because the term with the minus sign in the commutator cancels this term, and the derivative term, the two derivative terms now also cancel because you can see that they come with the opposite sign. And then that leaves us with the covariant derivative plus the remaining term of the uncancelled term from the commutator. And when you write that out infinitesimally, you can rewrite it as the transformed covariant derivative acting on psi, which is the infinitesimal version of this transformation, which I've written in the more suggestive form because that's the more general statement that we were after, which is that we want the covariant derivative to transform in the same representation as psi itself. And therefore the Dirac Lagrangian with the covariant, and so that therefore the covariant Dirac Lagrangian is gauge invariant. Now, that establishes that if we take a system of some number of fermions transforming in some representation of some subgroup of UN, then we can take that representation, and so let me say again. So if n is the dimension of some representation of some group, then we can couple fermions to gauge fields and gauge that symmetry group. In our example, we just looked at the fundamental representation of SU2, but we could have actually, instead of looking at the fundamental representation, we could have looked at any representation of SU2. And then, instead of the looking at the generators in the fundamental representation, we could have put the generators in whatever representation we chose. Because the proof of the gauge invariance didn't rely on the properties. It didn't rely on the fact that we're using that particular representation. It actually just relied on the SU2 algebra itself. So we've established that given a group and a representation, that we can write down a gauge invariant fermion Lagrangian. But that whole procedure involves introducing all of these gauge fields, one for every generator. So we have to think about then their kinetic terms. And we showed how to construct gauge invariant kinetic terms. So let's review that. So when we formulated electromagnetism, we formulated it in terms of the F mu nu, the electromagnetic field strength tensor. And what we're going to do is then construct a non-abelian analog of that. And that comes by generalizing this property that if psi is a field with electric charge E in electromagnetism, then the commutator of the covariant derivatives acting on psi is proportional to F mu nu acting on psi. So F mu nu is actually naturally the commutator of the two derivatives. Now, in the non-abelian case, we have this property that d mu psi transforms as u times d mu psi. And so the commutator also transforms in the same representation. The commutator acting on psi also transforms in the same representation. And in fact, the commutator transforms in the representation in which you multiply on the left by u and multiply on the right by u dagger. This is called the adjoint representation. So you see, applying that to psi, the u dagger would cancel the u in the transformation of psi. And we use that to define what we mean by the generalized non-abelian field strength. So we just extract the components of the commutator of the covariant derivatives and an appropriate factor of I and G. And those components are the components of the field strength tensors. And at the bottom, we've got two explicit formulae two explicit formulae for the case of SU2. Now, because we already have that we know the transformation law of F mu nu transforms in the adjoint representation. So the F mu nu, individual F mu nu i's are clearly not gauge invariant because they carry an SU2 index I. But the trace of their Lorentz invariant products is gauge invariant, and we use that to construct the kinetic terms. And the way that we've normalized everything, that kinetic term will be, we'll take that product of traces and multiply by -1/2, and we do that in order to get the -1/4 normalization that gives the canonical normalization of the kinetic terms of the gauge bosons. So in other words, the Lagrangian is just direct sum of Maxwell type Lagrangians. And in the general case, everything we've said goes through as long as we consider compact gauge symmetry groups. In other words, if I write the exponential form of the group matrices in a given representation as e to the I alpha t, where the alphas are real, then the t's will be Hermitian matrices. And then the possible groups that are allowed will be of the form, will be unitary or special orthogonal or symplectic, or there are some exceptional groups called G2, F4, E6, E7, and E8. And a general gauge theory will have a gauge group which is made of these groups. So you take, these groups and products of these groups with themselves. And that would be the general form of a gauge group in a gauge theory. And essentially everything goes through in the calculations that we did for SU2. We just have to replace the SU2 generators by the Hermitian generators of whatever the gauge group is we're talking about. And we replace epsilon I jk by the structure constants of the corresponding Lie algebra. And the corresponding formula for the field strength is given below. And for such groups, it's always true that the trace of the product of any two generators is zero if the generators are different, and is given by this formula here, where C of R is a constant which distinguishes the representation. Essentially, it's the Casimir of the given representation. And this Lagrangian is called the Lagrangian for Yang-Mills theory, or non-abelian gauge theory. And the A's are sometimes called the Yang-Mills gauge fields. So an important point about, from a physical point of view, about these Lagrangians is that non-abelian gauge fields interact with themselves, because when we expand, since F is schematically dA plus coupling constant times A squared, when we expand out F squared, we get two types of interaction terms. One is a cubic interaction proportional to G, and the second is a quartic interaction proportional to G squared. And those interactions are extremely important. So, for example, this pure, for most of the gauge groups I was talking about, most of these groups these self interactions create highly non-trivial effects at low energies and mean that the forces between particles transforming under these gauge symmetries become very strong at low energies. And that leads to the phenomenon like quark confinement, for example. The reason that quarks like to form mesons and baryons like protons and neutrons. Okay, so that was the brief review of what we did last time. So it's really important that you are able to go through the calculations which demonstrate that those Lagrangians are gauge invariant. What we're going to move on to now is the standard model Lagrangian. So we've covered relativistic wave equations, the Yang-Mills Lagrangian, and the Dirac Lagrangians and gauge symmetries. And that's most of the tools required to understand, at least at the classical level, the Lagrangian for the standard model. So that will be our final topic. So what we've seen is that if given a gauge, if someone gives us now a gauge symmetry group G and a set of generators of some representation of G, then we can write down the Dirac, the covariant, well, we can write down the covariant derivative acting on Dirac spinor fields in that representation. And from that, we can build the gauge invariant Lagrangians that we were just talking about. And so, from a mundane point of view, the standard model is just a particular gauge theory with a gauge, particular gauge group, SU3 times SU2 times U1, and a bunch of fermion fields transforming in various representations of that group. So in principle, we're now in a position to write down the Dirac part of the Lagrangian and the kinetic terms for the gauge fields. So let's look at some of that in more detail. So in this formula below, we're suppressing the matrix indices on the generators. So, the TRs are a set of generators in some representation. So they have matrix indices, and psi itself has matrix indices. So we can write the formula with the indices included here. So just to emphasize that we shouldn't forget what the formula, what the more compact version actually means. So the indices A are the ones which run over the generators of the group. So A goes from 1 to the dimension of whatever the group is that we're talking about. And the P's and Q's are the representation indices. So they go from 1 up to the whatever the dimension of the representation is. And I also put in alpha, which are the spinor indices on the spinor field psi. And we also have an additional choice that we can make, which is we can take psi to be purely left-handed or right-handed. So we have to we can pick a representation for the left-handed part of the spinor field, and it could be a different representation for the right-handed part of the spinor field. And so we use gamma 5. We can use gamma 5 to make that distinction. So in particular, we can define these projection operators P left and P right, which satisfy the relations below, that if you act with P left on a Dirac field, it will project you onto the purely left-handed component of that field, and similarly with P right. So, for example, if you wanted to define a covariant derivative for left-handed fermions in some representation of G, then that would be defined by inserting the left-handed projection operator into the covariant derivative itself. For those of you that want to play around with this a bit more, Peskin and Schroeder in section 19.4 give a few more details of other ways of, maybe they play around with these Lagrangians a bit more, and sometimes that could be useful. So if we, for example, focus on the electron field, so it's common in the textbooks to use the sort of symbol for the particle to denote the field often. So E here is actually the Dirac spinor corresponding to the electron, which I've written as, E left, E right. Then what we mean when we write down the covariant Dirac Lagrangian for the electron will be the left-handed term and the right-handed term. That's these two terms over here. But in general, as we will see, the left-handed and right-handed components of the electron transform in different representations of the gauge symmetry. So you see here, we're distinguishing the representations for the left and right-handed pieces. So it's really important to remember when you see the covariant derivative or the kinetic term written down, one has to be able to interpret it correctly, and to do a calculation. Okay, so after the break, we will and then look at the standard model gauge group and the representations for the fermion fields in the standard model. So we'll come back at Q2. Sorry, at 5:02, because we're basically at 45 minutes. Pause. I always forget that. Okay, so the gauge group of the standard model, at least locally, is SU3 times SU2 times U1. So we've met all of these groups in different contexts during the course of the lectures. So the SU3 part of the gauge symmetry is associated with the strong nuclear force, and the SU2 times U1 part is what's called the electroweak part of the standard model. Notice that this U1, the U1 factor in the standard model gauge group is often denoted U1y, and is also that U1 factor is also called U1 hypercharge, just for historical reasons. And that U1y is not the U1 gauge group of electrodynamics. The Maxwell U1 is actually a subgroup of SU2 times U1y. And we'll see which subgroup it is a bit later. So if you remember that the standard model fermion content consists of 3 families of quarks and leptons, and it's just a fact that each family transforms in the same representation of the gauge group. And that's partly why they call them families. Now, each of these families contains 15 fermions. So if we look at the first family, we've got the left-handed neutrino. So there's one of those. Left-handed electron, there's one of those. Right-handed electron, one of those. But then for the quarks, there's not just one up quark. There's not just one left-handed up quark and one right-handed up quark. There's actually 3, because each of the quarks transform in the fundamental representation of SU3. So that's why there are 15 of them. I mean, that's why there are 15 fermions in a given standard model family. There's actually 15, there's actually 30, because you have the 15, but plus you have the antiparticles. Okay, so let's talk about, let's try and understand which representations these 15 particles transform under. So let's establish some notation first. We're going to write a given representation of SU3 times SU2 times U1. We'll write it as R1 comma R2 with a subscript Q. So R1 is a representation of SU3, R2 is a representation of SU2, and Q is a representation of U1. Now remember that the representations of U1 are just given by integers. So Q will just be an integer for each standard model representation. However, in the physics literature, one divides by a factor of divides this integer by a factor of 6, usually. So I'm going to stick to the physics notation. So the Q's will typically be some rational numbers. And we'll use a notation in which R1 and R2 are denoted by their dimensions. Hopefully it will become clear as we go along. So this is the representation that the 15 fermions of a given family transform under. So there are 5, it's the sum of 5 irreducible representations. So what does this mean? So for example, here, 1, 1 means that whatever this field is, it transforms in the trivial representation of SU3 and the trivial representation of SU2, because both the entries are 1 and the trivial representation is one-dimensional. However, this field has a hypercharge which is -2. Here we have a field which transforms in the fundamental representation of SU3, but does not transform under SU2 and has some specific hypercharge, 4/3. These are the only fields which transform both under SU3 and SU2. Does anyone have any questions about this notation, or what I mean? Yeah, what I mean by these representations, or any other questions? Oh, there's a question in the chat. So why do fermions why do they have to transform? What is making them transform? Well, if they didn't transform, then they wouldn't interact with the gauge fields, as we've said. And you could have fermions out there which don't transform under any gauge symmetry, but they would be very difficult to detect because they don't interact with any gauge bosons, which means they don't interact with any of the known particles. So they would only interact gravitationally, and that would be the only way we could detect them. In a sense, we have detected all of these particles, all of these quarks and leptons, because they interact with gauge fields. And so almost by construction, they have to have interactions in order for us to observe them. And it turns out that this is how they interact. Their interactions are determined by the symmetries. Does that answer your question? Okay. I mean, that's a fundamental point. You see, when we write down when we looked at, for example, the little calculation we did earlier about gauge invariance of the Dirac Lagrangian, that up to an overall constant, it fixes the interaction term completely. So And that constant is just the coupling constant, the gauge coupling constant, G. So once you measure, if you find a way of determining G, you determine the interaction Lagrangian uniquely, because that gauge invariance fixes it. So that's a more general principle. One can, for example, one can define the standard model as a gauge theory in 4 dimensions with a specific gauge group, SU3 times SU2 times U1, and fermions which transform in this representation on the slide. And in addition, there's also some scalars, the Higgs scalars, which we'll come to later. But once you define that, you just write down everything which is consistent with the gauge symmetry, and then try to determine the coefficients of the different terms in the Lagrangian through experiments. Okay. So the 15 fermions transform in this particular 15-dimensional representation, and I hope it's clear what is meant by this representation. That means we can assign the 15 fermions to these 5 representations. And the way that is done is here. So 6 of the fermions, namely U left and D left, pair up into this doublet that we've mentioned before. But because they're quarks, they also transform under SU3 gauge transformations. And they have hypercharge 1/3. 2 of them pair up as the left-handed Lepton doublet, which is this 2-dimensional representation here with hypercharge -1. Then we've got the right-handed quark singlets, I mean SU2 singlets, UR and DR, they have different hypercharges. And then finally, we've got the right-handed electron. So notice there's no say right-handed neutrino, electron neutrino. But one could introduce such fields, and typically one does introduce them in order to understand models for neutrino masses and maybe other phenomena. So this is how the fields of a given family are assigned. And so let me actually copy this. So in the full standard model, if I include the other families, here you would have charm and strange quark and the top and bottom quark left-handed components. Oops. And then here you would have the other lepton doublets. Muon, left-handed muon neutrino, left-handed muon, and then same for the tau. And then here you'd have U right, C right, T right, and here you would have D right, S right, and right-handed bottom quark, and here you would have right-handed muon and right-handed tau. So that's all of the fermion sort of fermion quantum number assignments, if you like. Now, in the first family, only the only representation where the SU2 transformations are non-trivial are these ones and these ones, which means that only these left-handed fermions and their antiparticles interact with W bosons. So right-handed quarks and leptons do not interact with W bosons. And the antiparticle statement to that is that left-handed antiquarks and left-handed antileptons do not interact with W bosons. So when we talked a little bit about W boson decay some time back, W boson of charge +1 can decay into a positron and a neutrino, an electron neutrino. Now that electron neutrino is left-handed. That positron is the right-handed antiparticle of the left-handed neutrino. Because when you did that exercise for calculating the different terms in the SU2 Dirac Lagrangian, if you had put in just left-handed Dirac fields, you will see that only the left-handed particle and the right-handed antiparticle appear in the vertex. And similarly here, we have a left-handed electron and a right-handed antineutrino. And those sorts of phenomena are important because one can actually measure the handedness of these fermions under suitable conditions. So as we've mentioned, the quarks all transform in the fundamental representation of SU3. So the generators of that representation are Hermitian traceless 3x3 matrices, which are often called lambda A. Now you can choose whatever basis for those matrices you like, but there's one which is used in the physics literature called the Gell-Mann basis, which you can look up if you want. But anyway, the point I wanted to make is that since there are 8 generators, the space of Hermitian traceless 3x3 matrices is 8-dimensional, or if you like, the dimension of SU3 is 8-dimensional. Therefore, there are going to be 8 gauge bosons associated with the SU3 interactions. I'll denote them by G mu A, and these are the gluon fields of gluon gauge field, if you like, and the particles associated to them are the gluons. So in addition to those 8, we have 3 SU2 bosons, the W bosons, and we've got the U1 hypercharge, which is, since U1 is one-dimensional, we have 1 gauge boson, the hypercharge gauge boson, usually called B mu. So in total, there are 12 gauge bosons in the standard model. So now that we've got the, let me write a slide on that. So since we've been given the representations, those 5 representations, we can calculate for example, the Dirac terms in the standard model Lagrangian. And for that, we just need to know, the most important part now is just how does the covariant derivative, we have to treat the covariant derivative carefully. Because, you know, we go over here, the covariant derivative acting on the quark doublet, U left to D left, is going to be different to the covariant derivative acting on, say, the right-handed electron. You see, the right-handed electron interacts only with B mu. It doesn't interact with the gluons or the W bosons. So it only interacts with B mu, which is very different to the quark doublet covariant derivative. So when I say we have to be careful with the covariant derivative, that's what I mean. Is you have to look at what field you're calculating the covariant derivative on and know which representation that field is transforming in, and then you put the generators in carefully and you can calculate d mu acting on that field. In a sense, the covariant derivative of the standard model is one of the most important things that one needs to know how to work with. Was there a question?
Okay, Professor?
Hold on a second, let me turn the volume up. Yeah.
Okay. If neutrinos were found to be Majorana particles, would that change their representation under the symmetry?
Well, it would mean that we would probably have to introduce the right-handed neutrinos and introduce a Majorana, what's called a Majorana mass term for the neutrinos, but I haven't told you what that is, but you can look it up. Yeah, it would essentially imply the existence of the right-handed neutrino. Sometimes in the literature, the right-handed neutrino is called sterile neutrino because it doesn't have any, it doesn't interact with any of the standard model gauge bosons. It's in the trivial representation of the gauge group.
It is said that Majorana particle means that the right-handed neutrino would be the left-handed antineutrino. So, all this...
That's true, yes, that's true, yes. You can write a... Yeah, so that, yeah. another way of thinking of it is you can introduce a higher dimension operator with an explicit mass term, this operator called the Weinberg operator. But in order to understand that, we have to introduce the Higgs field. So yeah, there's a question of whether or not you think of the standard model Lagrangian as being fundamental or an effective description of physics. Okay, let's get back to the covariant derivative. So what I was saying is that we have to know how to apply the covariant derivative carefully. So for instance, let's look at the covariant derivative for the lepton doublet. Well, the lepton doublet, because it's a doublet, it transforms under SU2 as a doublet. So its covariant derivative includes the SU2 gauge bosons. And so that, this term just acts in the two-dimensional representation on these two fields, nu and E. In addition, because the lepton doublet has a non-zero hypercharge, it also interacts with the hypercharge gauge boson B mu. And we put a coefficient there in brackets y, which is the hypercharge of the corresponding field. And as we've defined it, the hypercharge is -1 for this doublet. On the other hand, we can look at the right-handed up quark, and we see, from its representation, it transforms in the 3,1 representation with hypercharge 4/3. So that means that there's no coupling to the SU2 gauge bosons, but there is a coupling to SU3 gauge bosons, the gluons, and a coupling to the hypercharge gauge boson with charge 4/3. So where is it? So this is the terms which reflect the fact that U right transforms in the fundamental representation of SU3, and this is the term which reflects the fact that it transforms under U1 hypercharge, and you just set Y in this formula equal to 4/3 to get the right interaction term. Are there any questions about that? So in principle, you should be able to calculate the covariant derivative of any of the standard model fields now. Okay, sounds like it's clear.
I have one question. So what if the coupling constant G1?
Hold on, Tron. Just a sec. Say again.
Yeah, I just wonder if we are allowed to set different values for the coupling constants for each type of particles. So, for example, if for charged leptons, you can set G2 different values from that of, for example, quarks.
No, you can't, because you see, then the Lagrangian will not be gauge invariant. You see that because the Dirac part of the Lagrangian would be gauge invariant, but the kinetic terms of the gauge fields would not.
Yeah, that's right.
Okay. That's a good question. Okay. So that's the covariant derivative of the standard model, and so in principle you should be able to calculate the Dirac terms in the Lagrangian. Now, what about electromagnetism? So I want to explain just very briefly, and then we'll continue with this next time. How does electromagnetism emerge from the standard model? Because so far there's been no mention of any photons. Well, the picture is that, you know, SU3 times SU2 times U1 is the gauge symmetry group, but that's a gauge symmetry that's manifest above a certain energy scale, which is called the electroweak scale. And below that scale is, you know, it's roughly 100 proton masses or so. Or around, you know, like 100, is of order 100 GeV. Below that scale, there's a mechanism called the Higgs mechanism, which breaks the gauge symmetry from SU2 times U1 to U1 of electromagnetism. So I mentioned before that U1 electromagnetism is a subgroup of SU2 times U1Y, which means that some linear combination of SU2 and U1Y generators must give the generator of electromagnetic U1, which is just the charge. So this is the formula in the middle, in the way that I've set up the standard model at least, gives you the relation. So the electric charge is given by 1/2 the hypercharge plus sigma 3/2. And from this point of view, it means that, you see, the direction in the Lie algebra of the standard model, in the direction of hypercharge, corresponds to the gauge boson B mu. The direction sigma 3 corresponds to the gauge boson W3 mu, and the direction corresponding to electric charge corresponds to the photon. So actually what happens is that B mu and B mu plus W mu, suitably normalized, become the massless photon field. And the opposite linear combination becomes a massive W boson, a massive gauge boson called the Z boson. So next time we'll study this a little bit in more detail. And you can, let's see, if I've done everything correctly, we should be able to calculate the electric charges based on the different representations. So for example, if you take half of this hypercharge, you'll get minus 1/3, and that's the electric charge of the down quark. Or if you take half of this hypercharge, you get the electric charge of the electron, and so on. And you can add in the other, you can compute the electric charges of these three fields as well, if you like, using that formula. Okay, so next time we'll look at the symmetry breaking, at least at the classical level, symmetry breaking in the standard model a little bit, just to complete the picture. Stop the recording. Are there any questions?
I wonder the way to calculate the hypercharge. So is it originally from the fact that we can measure the electric charge and we know the eigenvalues of the sigma 3 acting on the particles, so we calculated the hypercharge? Or is it some other ways to measure it?
You're asking that historically what happened? How did we get this formula?
Yeah, the
Maybe.
hypercharge.
Well, what happened historically was that I mean, this is kind of a longish story, and I haven't really taken the historical point of view in the course, but by looking at, for example, different particle decays, like meson decays, yeah, like looking at meson decays, one got the idea that, so sort of an intermediate stepping stone to the standard model was the Fermi theory. And so that's the theory which is effectively treating, you know, it's a sort of an effective model for treating particle interactions in which, so like at the moment, you know, yeah, let me just look at some, yeah, you have processes like this involving, say, W's and Z's, and here's some fermion 1. So this is some fermion current, and this is some other fermion current. So you could call this J mu prime. And I put W and Z in the middle because these are massive. And because they're massive, you can sort of integrate them out, and this becomes like a 4-point fermion interaction. So the Lagrangian here would just be J mu prime with some coupling constant, which actually is called the Fermi constant. And this type of interaction Lagrangian is responsible for essentially all of the phenomena involving fermions in the standard model. For example, decay of heavier fermions into lighter ones. Can be described very precisely by that Lagrangian. Decays of like mesons and baryons and so on. Once you try and put all of that together, but viewed from the point of view of this like effective theory with these so-called contact interactions, you started looking at these coefficients, which turned out to be, they turn out to be universal. And then that led to the idea that there were gauge bosons being exchanged. And these types of measurements, like these decays and so on, as well as evidence from neutrino experiments at CERN, gave some like indirect evidence for the existence of these W and Z bosons. And then it was a matter of time before someone, people wrote down an actual model based on a gauge theory. So that was the Salam-Weinberg model. Does that answer your question?
Yes, part of it. But I mean, historically, we know the chart of the particles, and
yeah, of course, yeah,
we calculate the Higgs charge, right?
Of course, yeah. But until you postulate what the gauge symmetry is and what the symmetry breaking pattern is, you can't get a formula. So yeah, of course we knew the electric charge first.
Yeah, thank you. That's clear.
When you go on to study the standard model properly, as in the courses later, you can you can read about these current interactions and how you build up the evidence, different types of evidence which leads to the actual symmetry structure. Is there another question or comment? Did I not confirm what the homework was for tomorrow's tutorial? Was I a bit, or was it clear or not?
I think you did set the problem until that one about breaking the symmetry, but I don't remember the page.
Okay, let's have a look. Oh yeah, that's right. Symmetry breaking from the Lagrangian, is it? Here, you mean?
Yeah, that one.
Okay, so then I know it's a bit late for tomorrow. No, that was this. So up to here is for tomorrow, right? Is that the point?
Yeah, basically the deadline for submitting these are tomorrow.
Okay. So then for the next, the next set, we'll define it on Thursday then. But whatever's left in these notes, any questions I've set there will certainly be part of it. And I'm yet to put any questions in for today's lecture. All right, so see you on Thursday, which will be the last actual lecture.
Can I ask, so after next week, that's the last tutorial, and the next week we will have final exam, is it?
No. So yeah, there'll be some tutorials next week. I've got to decide which days, which exactly when they will actually be, but we'll let you know. Then the week after that will be your quantum mechanics exam. Okay, and then the week after that, which is like second week of November, will be my exam. Is that clear?
Yeah.
At least that was the plan that I had set with Narayan. So that you have basically, you'll have like you'll have, I mean, he'll probably set the exam at the end of that week, and I'll set my exam at the end of the following week. So you have like 1 week each to focus on, first quantum mechanics, and then you can focus on field theory. So it makes it easier.
Professor, I wanted to ask, how will be the format of the exam?
It's going to be a written exam.
So like a live session, or?
Yeah, I think it's going to be, well, I don't know about Narayan's exam, but usually he does written exam. Look, I'm intending to do a written exam, so there'll be a room, and you come into the room and you sit there and write. Okay. I can't remember how long the exam is supposed to be, but I'll let you know. Yeah, I'm not sure how much.
Students who are still at home, they will attend the exam the same day.
Oh yeah, so we have to work that out as well. Yeah, so it'll have to be done simultaneously. It's a bit. So are there actually students still literally at home and not in an institute? Sorry, because I hadn't thought about that. But who is actually at home?
I'm at home now.
Who said that?
I'm also at home,
Me,
Professor.
Gustavo.
Hang on. Raise your hands on the chat thing or whatever if you're at home, so I can see. I don't see any. Can you not raise your hands?
I don't know how to raise the hand, but it's me, Gustavo.
Okay, I'll go through one by one. Gustavo, Acharya, where are you? Acharya is not answering.
I'm at home, Professor.
Okay, but you can go to the institute, right?
I'm not sure about that. I'm still at home. The institute is far away from me.
Oh, where is your home, Acharya?
I'm in South Sudan.
Oh, sorry. So you didn't. Okay, you're not in Rwanda at all. Okay.
Yeah.
We'll have to figure it out in your case. Okay.
It's okay.
Who else do I not know about? Okay, Nadima, you're still in Iran.
Yes, Professor.
Okay, this is going to be complicated. And so, where is the? All right,
Alan.
Oh, Alan. Where are you, Alan?
I'm at Honduras, but I'm supposed to be to arrive at ICTP this Saturday.
Okay, let me check. Oh, so then, yeah. Saturday. Do you know what your quarantine requirements are from there? Do you know how long you would have to do self-isolation or whatever in the room, if any?
I guess that it will be as the rest of us, that will be for 10 days. So it might be isolated also the same amount of time.
Okay. This whole thing is a mess. But we will try to resolve it one way or another. Yeah, I mean, you know, one possibility is for those of you that are not going to be in this room, or whichever room is the room where the exam is going to take place, that the others make sure that they're on, you know, on Zoom, so we can see. So you're sort of here virtually, and you do the exam at the same time. I think that potentially could work. And the ones that are able to go to the institute in Rwanda, they can set up the exam there at the same time. Anyway, thinking about coordinating all of this is giving me a bit of a headache. So I have time to work it out. Also, Narayan will do his one first, so we'll see how his goes. But I'll talk to Narayan as well about it. But yeah, I mean, most likely there'll be, you know, in my exam, you know, some shorter questions and then some longer ones. I haven't quite figured out exactly. I have to think. I mean, I haven't really thought carefully about the structure and the length of it yet, but I will do. All right, so take care, everyone, and I'll see you on Thursday, if not before.
Yeah, thank you, Professor.
Thank you,
See you.
Professor.
Thank you. See you.
Thank you, Professor.